to have Mark Zhandry here. So Mark's spoken at the colloquium before, so I'm sure many of you know about him already, but Mark started his career as working in cryptography, in classical cryptography, but he's been, over the years, he's worked a lot on the quantum, on the foundations, the quantum foundations of cryptography, or the foundations of cryptography in a quantum world. And at this point, I think we can safely say he's as much of a researcher in quantum information science as anybody else. So today he'll talk about a very exciting new paper that he just posted on verifiable advantage without, in the absence of structure. So Mark, really looking forward to this talk.
All right, thank you for the introduction. Let me start the share. All right. Right, so today I'll be talking about a very recent work with Takashi Yamakawa on verifying quantum advantage without structure. So this talk is timed for about 45 minutes, so there should hopefully be plenty of room for questions. So I'll try to pause throughout and answer questions as they come up. Also, I know this is a quantum colloquium, but in case anyone is watching maybe less familiar with quantum computation, I'll try to keep the talk pretty accessible. So before diving into the results, let me spend some time to clarify what we mean by all these terms and to give a short survey of prior work and also to motivate the setting for our results. So we start with the defining question of the field of quantum computing, which is, do quantum computers give speedups over classical computers, also known as advantage? For this talk, we are not interested in Grover type speedups that achieve polynomial advantage, even though such speedups are, of course, super important in practice. But where super polynomial speedups shine is that they allow quantum computers to completely crush the classical competition by solving a problem quickly that classical computers won't be able to solve until well after the universe ends. This will be our goal. Now, if we have a quantum computer, we would ideally like to know that it is actually solving the problem it is supposed to. We would actually like to verify that it is, doing something quantum. And verification is also fundamental to quantum computing, as ultimately we want quantum computers to have real-world impact. Observing such real-world impact really is a form of verification. If quantum computers are better at simulating chemical reactions, we'll see this through, say, the utility of drugs that we can design as a result. If quantum computers can break cryptography, we'll see this through security compromises. If quantum computers are better at machine learning, we'll see this through improved artificial intelligence. In many cases, such as with cryptography, the verification that we get is entirely a classical algorithm. In general, though, if we assume the universe is at least a quantum Turing machine, if the universe can verify, as evidenced through the real world impact, this at least means there's a quantum algorithm for verification. A particularly important question is whether there is quantum advantage in the complexity class NP. NP is the most important class of hard problems in computer science, and it's the class of problems whose solutions can be verified efficiently without interaction on a classical computer. These capture many, but of course not all, of the most important problems people care about. Okay, so now we're going to define the last term, which is structure. Structure has long played a central role in proposals for quantum advantage, in the sense that structure seems to be what separates problems that have super polynomial advantage, such as factoring, from those that don't, like NP-complete problems. Now, structure isn't well defined, and there are surely many reasonable ways to talk about structure for quantum advantage. In this talk, I'll take a complexity-theoretic view of structure, motivated as follows. Any setting that requires any setting for quantum advantage requires certainly a fast quantum algorithm, but it also requires a lower bound on the running time of any classical algorithm. And the sad truth is, with the current state of complexity theory, we can't hope to prove such good lower bounds for classical algorithms. So we need some extra piece of help, and there are really two main approaches. The first is an oracle separation, where we specify some oracle, some function, relative to which we can obtain a quantum advantage. And this function can only be accessed through oracle access. Classical algorithms can, of course, only make classical queries to this oracle. So they send a classical X and get f of X in response. But quantum algorithms can now make quantum queries on superpositions of inputs. Introducing oracles helps essentially because we can actually prove lower bounds on the number of queries. And a lower bound on the number of queries in particular implies a lower bound on the runtime. So the hope is to find an oracle where the so-called query complexity of some problem gives a super-polynomial gap between classical and quantum. Now, in order for our separation to be the most meaningful, we would naturally like to have the simplest or least structured oracle possible. What is the minimal structure here? Well, it seems clear. It seems that a uniform random oracle is the minimal structured oracle because essentially by definition, it can't have any special features. So in oracle separations we'll take structure, or we'll take the lack of structure to mean a random oracle. The other approach is to simply conjecture some classical hardness by making a computational assumption. Now we would naturally like the minimal possible assumption and one that is most widely believed so as to get results that are as close as possible to unconditional and therefore most likely to be true. There are a wide variety of possible assumptions that can be made. And while these assumptions are in general incomparable, we can do some reasonable partial ordering. On the far left, we have unconditional results, the Holy Grail, which, as we just said, are out of reach. Another common assumption is that P is not equal to NP. If we want quantum advantage for an NP problem, we certainly must assume at least that P is not equal to NP. But we may have to assume more. So we're at least stuck to the right of P not equal to NP. Moving further to the right, we eventually get to the assumed existence of symmetric key cryptography. This is basically the minimal requirement to do secure communication in most classical assumption. As we move further still, we eventually get to classical public key cryptography, the backbone of the modern internet. And as we keep moving right, we start seeing famous number theoretic problems such as the hardness of factoring, discrete logarithms, pairings on elliptic curves, learning with errors, or LWE. There's also maybe less famous examples like the hardness of isogenies between elliptic curves. You may disagree with me on the exact ordering between these problems, but the hardness of all of these problems implies in particular public key encryption, so certainly they fall to the right of public key crypto. So in this second option for conditional separations, the concept of structure is definitely more squishy than the oracle case. And as a rough definition, what we're going to take for structure is to mean the assumed classical hardness of the problem is not known to imply classical public key encryption. The justification for this is exactly that all the assumptions that imply public key encryption are algebraic assumptions with significant algebraic structure. In contrast, say symmetric key crypto, we can build symmetric key cryptography from functions whose sole job it is to scramble their input, essentially functions whose job is to mimic random oracles. So we have a strong correlation between algebraic structure and the ability to build public key encryption. And our two notions of structure for the oracle and conditional setting are very closely linked. In one direction, given any result relative to a random oracle, we can heuristically instantiate it using a concrete cryptographic hash function such as SHA-256, giving a plausible conditional construction from just symmetric key tools. And there's a long history of cryptography of modeling cryptographic hash functions as random oracles to understand their security properties. So this heuristic is very well studied. There are counterexamples to this kind of heuristic, but they're always contrived and tend to have a little impact on real world applications. And another supporting evidence for our notion of structure is that Pagliazzo and Rudich showed that random oracles alone cannot be used to construct public key encryption. Meanwhile, random oracles can be used to construct most of symmetric key cryptography. So really, there are two notions of structure are quite compatible with each other. I'll just briefly mention an aside that's not relevant for this talk, but it's just a fascinating and open question, is that it is not known if random oracles imply public key encryption, where encryption and decryption may be quantum, but communication is still classical. I mean, this is why I keep saying that random oracles cannot give classical public key encryption. We don't know if the analogous result holds or not for quantum. And I think this is a extremely interesting open question. Maybe I can pause here to see if there are any questions.
So Mark, can you repeat what you said at the end? What is not known from random oracle?
We don't know if using quantum computation locally, but classical communication, we don't know if you can build public key encryption from random oracles.
Got it. Okay.
There's some work on this that is hinted that the answer is that you can't, but we haven't been able to actually lift the Impagliazzo-Rudich result to the quantum setting.
Yeah.
Are there any other questions? Okay, I'll move on. So we can summarize the prior work in the following picture. So we can categorize the prior justifications of quantum advantage according to whether they are verifiable and whether or not they are structureless. The earliest justifications due to Bernstein and Vazirani and later Simon gave oracles separating BQP from BPP. These problems could be verified. However, the oracles were highly structured, both utilizing some form of periodicity. Basically, such periods can be observed quantumly, but remain hidden classically. Not long afterward, we get Shor's famous algorithm for solving factoring in discrete logarithms, which are presumably hard for classical computers. These two are verifiable and don't involve oracles, but they do imply public key encryption. And this is, the main danger of Shor's algorithm is the fact that they can break much of the public key cryptography we use today. Shor's algorithm was followed by Halgren's algorithm for solving Pell's equations, and as well as Babai et al.'s algorithm for matrix group membership. And what's interesting is that all these examples of non-relativized verifiable advantage are for problems whose classical hardness can be used to build public key encryption. At a technical level, these works all operate by giving highly non-trivial reductions from the stated problems to finding the period of some periodic function. In other words, they can be seen as real-world instantiations of periodic oracles. On the other side, we have a problem called Fourier sampling or Fourier fishing proposed by Aaronson. This is a problem defined relative to a random oracle and therefore structureless, which is easy for quantum computers, but unconditionally hard for classical computers. And then below that, we have standard model results by Bremner and others, which basically show that simulating the output distribution of a quantum circuit is classically hard. And these results follow under plausible general complexity-theoretic conjectures and are also therefore structureless. Right, and neither of these problems on the right are known to imply public key encryption. However, in both cases, verification is intractable. And actually, verification costs essentially as much as classically solving the problem. And moreover, verification it plausibly even remains hard even if you have a quantum computer to do the verification. One more result I'll briefly mention is a recent, somewhat more recent work of Regev et al., which I put on the edge of the verifiable bubble since they give an interactive protocol as opposed to a non-interactive problem like an MP statement. So it's a little bit weaker in terms of the verifiability. What's quite fascinating about this one though is that LWE, the underlying assumption of this protocol, appears to remain hard for quantum computers. And so it's quite surprising that you can get quantum advantage out of a problem that is actually not believed to be quantumly easy. There are, of course, tons of other results in the literature, and I won't really mention them, but to the best of my knowledge, the results here are representative of the current state of affairs. And where our work shows up is in the intersection of these two bubbles, which was previously empty.
Mark, can I ask a question?
Yeah.
Could you say that? Yes. I didn't understand that statement saying that it's surprising that you can get an advantage for a problem that's considered to be hard for quantum. The advantage is that it's hard.
Right. What I mean is that, so what is quantum advantage? At least for the context of this talk, quantum advantage means something that's classically easy but quantum hard. And with LWE, we believe it's it's classically hard and also quantum hard.
Oh, I see. So you're saying you're getting this verifiability of quantum hardness from a problem that itself is quantum hard. Okay, so that is the conundrum there. Okay.
Yeah.
Can I also ask the question here? So
yes,
you want structureless. I'm trying to understand if I understand your motivation completely. So I understand if your motivation is, look, these assumptions, I don't know if I believe them. Of course, I believe kind of one-way function or symmetric encryption is a weaker assumption, and I want to kind of get quantum advantage from the weakest possible assumption. Is that your motivating goal, or is there something else that?
Yeah, I mean, as we'll see when we get to our results, we don't get a result that's like, one-way functions or some particular assumption that people have studied before. But the point is to understand the extent to which structure is needed for quantum advantage. And yeah, structure is not really well defined. The view of this talk is we're taking structure to roughly correlate with the strength of the assumption in terms of like implied cryptography.
Got it. So this is kind of a fundamental question you're interested in. It's not just about kind of, okay, got it. Thanks.
Right. Okay. Good. So before moving on to actually stating what our results are, I do want to just give a couple more remarks. So first, we observe that all non-relativizing NP problems demonstrating quantum advantage rely essentially on period finding. We just don't have a lot of techniques compatible with NP for giving a quantum advantage. And for example, the LWE proof of quantumness that I mentioned on the last slide, it doesn't give you an NP problem. So it doesn't rely on period finding, but it also doesn't give you an NP problem because it's interactive. Second, we observe that all structureless sources of advantage are basically sampling problems, where the task is to sample from a distribution as opposed to outputting a particular output or a member of a particular set. The distribution may in fact have non-zero weight on all inputs, which means that given a single sample, you actually can't determine if the algorithm is sampling from the correct distribution. You can, of course, turn such problems into more traditional computational problems by looking at lists of many samples. But the point is you're starting from a problem where verification is not really an inherent feature. And usually when you try to turn it into a problem of a search problem, you generally get something that's computationally intractable. Finally, I want to mention something called the Aaronson and Buis conjecture. So Aaronson and Buis investigated the relationship between structure and quantum speedups for a couple possible notions of structure, some of which differed from the kind of structure we're talking about today. But importantly for us, they write down a conjecture, summarized informally in the picture here, which roughly says that if you have any quantum algorithm A, which I've denoted in ket notation, that makes Q queries to a random oracle and outputs a single bit, that there is a classical simulator that makes only polynomially more queries to the random oracle and can approximately simulate the distribution of outputs. So this conjecture actually predates the work of Aaronson and Buis, going back at least to 2000. Now, there's no reason a priori for believing this conjecture, but it has been a central conjecture in quantum query complexity for some time and has remained unrefuted. Moreover, Aaronson and Buis show that this conjecture actually follows from a different conjecture, which on the face of it has nothing to do with quantum computing. It's some conjecture about the behavior of bounded low-degree polynomials. This other conjecture, it in turn is closely related to other results that have been proven. And so while while everything still remains a conjecture, here there is some good evidence that the conjecture may be true. So what's the implication of this conjecture? Well, if we think of a quantum algorithm as solving some decision problem efficiently, what the AA conjecture yields is a classical algorithm for the same problem that is query efficient. Now, and what this says roughly is that we can't hope to separate BQP from BPP just by looking at query complexity, but introducing oracles was kind of the whole point of separating complexity class was kind of the whole point of introducing these oracles and working in a query model. Now, it could certainly be that as the classical simulator is computationally inefficient, and you would expect this to be necessary if, say, A ignored its random oracle and factored integers or something like that. But demonstrating the computational inefficiency of S is essentially a non-relativized problem, defeating the whole point of using the oracle. So the takeaway is that to whatever extent you believe the Aaronson and Buis conjecture, random oracles don't seem to help in giving separation for decision problems in NP. Okay, and so with that, let's get to the results.
Mark, sorry.
Yeah.
What do you mean by approximately 0, 1? So this is a decision problem, right? And you're saying the output of S should be the correct answer with a high probability. That's what you mean?
Yeah. So let's say on a particular input, A outputs 1 with probability 2/3, then S should output 1 with probability, something a little less than 2/3, potentially, but close to 2/3.
Okay.
Right, and the conjecture is a little more precise than this. It also includes, it's actually poly Q and 1/epsilon, where epsilon is the error that you're willing to tolerate. I see.
So your point here is that so either I have to either this conjecture is bad news, or I need to assume something about a problem that a computationally unbounded S can solve, but a computationally bounded S cannot, which sort of takes us, what is that problem? That takes us back to.
It seems to defeat the point of looking at looking at a query model.
Okay, I see. Thanks.
Sorry, unless the conjecture is false.
Unless the conjecture is false, yes, and it could turn out that the conjecture is false.
Just one question. I mean, your left top bullet, all existing sources of advantage and rely on period finding. I was wondering if you thought about, rather than talking about NP, about things that are refutable. There's this sort of definition of refutability in crypto as a reasonable assumption. Something
refutability in what sense? Like co-NP?
In the sense that if it's false, you'll be able to kind of demonstrate the fact that it's false, but not necessarily with the written down proof. Like factoring is refutable. Factoring being hard is refutable, and other. It seems to me that that's what you're getting at when you're talking about NP.
Right. I mean, I guess I think about it in the language of like a protocol for verifying advantage, where NP corresponds more or less to a non-interactive protocol. And you could consider interactive protocols, and this is what the work based on LWE does, for example. So yeah, it's certainly reasonable to consider quantum advantage that doesn't correspond to an NP problem, but also I think it's pretty interesting to consider whether there is quantum advantage for NP problems.
So Mark, if I may, one more question. So the top left thing, right? I mean, you could take the LWE based interactive protocol, right, BCMVB, and try to Fiat-Shamir it into a 2-message protocol. But that you're saying that doesn't give you NP problems because it's 2-message.
You can't Fiat-Shamir it because it's not public coin.
Not all the way through, but some of it is public coin. All except the first message is public coin, right? Oh, I see. It's not publicly verifiable, you're saying. Okay.
Yeah, exactly.
And on the top right, could you take the structureless sort of sampling problem and have the prover actually run an interactive proof, convincing the verifier that it sampled correctly? And the problem is in P space probably. So you could run IP, but you're saying you need the prover to be efficient in BQP as well.
Right. Yeah. So certainly there are ways to take the sampling problems and try to turn them into verifiable problems, but it seems like it always ends up resulting in something inefficient.
Prover. Yeah, I see.
Yeah. Okay. So if there's no other questions, I will go on to what our results are. So here's our results. So we give the following results relative to a random oracle with probability 1. So first, we show that there are actually NP search problems solvable by BQP machines, but not BPP machines. And note the restriction to search as opposed to decision NP problems. Importantly, our instances are actually always trivially yes instances. So the decision problem is easy. And this is somewhat inherent unless we want to make progress on the AA conjecture, that if we're going to have an unconditional result, we can't be giving a separation for decision problems. And I don't know, I found this a little surprising, just because we often don't pay attention to the distinction between search and decision, and here it was actually very important. So next, we study the implications to cryptography, and we show that there are a number of crypto objects that are classically hard but quantumly easy, again, relative to a random oracle. These include one-way functions, collision-resistant hashing, and digital signatures. If we additionally assume public key encryption that is at least classically secure, we obtain a separation for public key encryption as well. That is, we can construct public key encryption that is classically hard but quantumly easy, whether or not the original scheme was quantumly easy. And note that for the public key encryption separation, assuming PKE is essentially required, since we know that random oracles alone cannot give public key encryption. The separations that we have trivially also yield this thing called a proof of quantumness, which is a protocol between a quantum prover, a protocol between a quantum prover and a classical verifier, where the quantum prover actually proves to the classical verifier that it is quantum. Our protocols have as few rounds as possible. Here, the minimal rounds depends on whether we consider uniform or non-uniform adversaries. For uniform adversaries, our proofs are non-interactive. For the next results, as we said, we don't make any progress on refuting or confirming the AA conjecture. So we still find it quite plausible that the AA conjecture holds. And under this conjecture, we show that we can lift our proof of quantumness to obtain certifiable randomness, again in minimal rounds. So what is a certifiable randomness protocol? It's a protocol that allows a quantum server to generate uniform randomness for a classical client. And even if the server deviates from the protocol, you still want to guarantee that the string produced by the classical client is random. And then a final thing, it's not really a result, but just a remark, is that we can get non-relativized candidate versions of all of the above results by replacing the random oracle with a concrete cryptographic hash function such as SHA-256. As noted already, there's a huge body of literature which models standard cryptographic hash functions as a random oracle anyway for the security analysis. And so we can make the heuristic assumption that security in the random oracle model implies security when instantiated with SHA-256.
Mark, can I ask you a quick question?
Yeah. Yes.
Every time when you say classically hard but quantum easy, you mean classically secure but quantum broken, right?
Yes.
Okay.
Yeah. Any other questions before I dive into the construction?
Just a question, more of a guess. Is the difference here between search and decision that with decision you can amplify your probability of correctness, and with search you don't?
Not really. Basically, you can think of basically what happens is we construct something you can view as a one-way function. that is very compressing. And so all possible elements in the codomain are actually images of the function. And so in some sense, the analogous NP problem, which is, given a element in the codomain, does it have a pre-image? That NP problem is trivially always yes, because every element has a pre-image. But it still remains, the function still remains one way, at least classically. And so that's why it's a search problem that's hard rather than a decision problem that's hard.
I see. And in that case, you do not have a reduction from, like the previous slide shows, from a query on a quantum to query classical.
Right. Yeah. So this Aaronson and Buis conjecture, it's sort of really fundamental to the conjecture that the output of the adversaries is 0, 1. And the reason is, it's maybe not as clear from the picture I drew here, but it has to do with the fact that this poly Q actually also depends on the error you're willing to tolerate. And if you have exponentially many outputs for your function, basically if you want S to actually simulate A, you need your error to be very, very tiny in order for it to be a meaningful simulation.
That's why I thought that it had to do with amplification. So if it was 0, 1, you could kind of amplify. If you have exponentially many of them, what's the chance you're ever going to see it again? Yeah. Okay.
Right.
So it works here. So you're saying the reason this works is that you can amplify, but the reason your thing works is entirely different. Yeah.
Sure. Yeah.
So Mark,
Yeah.
The publicly verifiable proof of quantumness, right? I mean, is it using oracles or not using oracles?
So except for the random oracle or the conjectured version with SHA-256, there's no oracles.
But there is a random oracle, really, right? I mean,
yes.
All right. Thanks.
Yeah, everything in this light blue box is relative to a random oracle.
And because it's not interactive. It's just one message. Yeah.
It depends on whether you're talking about uniform or non-uniform adversaries. There's a subtlety with non-uniform adversaries, but for uniform, it's not interactive. Okay, so let's describe our construction. So here's our hard problem. We start from a high-dimensional, large alphabet linear code that I'll call C. I'm going to use the terminology code since coding theory will be important in a few slides. But you can just think of this you can think of a linear code as just a linear subspace mod Q for some large integer Q. So here's a picture of some code. And obviously I can only draw 2 dimensions easily, but we'll think of our code as being very high dimensional, hundreds of dimensions. So to start, we'll start with something that's actually easy, but we'll start with the problem of simply finding a code word in this code. Since our code is linear, finding a code word just involves solving linear algebra. Regardless of the dimension, this is easy. So what we're going to do is we're going to make things slightly harder for the adversary. What we're going to do is we're going to choose a random subset of the x coordinates. Just every possible x coordinate will be in our set with probability 1/2. And now we will say that valid solutions are code words that must have an x coordinate belonging to the set of valid x coordinates that we chose. Right, so okay, I guess our alphabet will be exponentially large, so we cannot simply provide the set of x coordinates in the clear. And this is where the random oracle comes in. We'll interpret the random oracle as a set of x coordinates. That is, for each possible x coordinate, the random oracle will contain 1 bit. Valid x coordinates are those whose random oracle bit is, say, 0. We can therefore test if an x coordinate is valid by making a single query to the oracle. So we've made our problem slightly harder by eliminating roughly half of the code words from contention. Of course, the problem is still not all that hard. You can sample a random code word using linear algebra, and then just throw it away and start over again if the x coordinate happens to be invalid. In expectation, you only have to generate 2 code words before you find one with a valid x coordinate. So we've really only double the difficulty. You can still solve this easily in polynomial time. So what do we do? Well, we have other coordinates at our disposal. So now we do the same thing for the y coordinate. We choose another random set of coordinates that we are going to call valid for the y coordinate. We'll want our valid y coordinates to be chosen independently from our valid x coordinates. But this is easily handled just by using a slightly larger random oracle, where we split the random oracle in half, using one half to decide for valid x coordinates and the other half to decide valid y coordinates. So now we've made the problem of finding a solution slightly harder still, as a random code word will simultaneously have a valid x and a valid y coordinate with probability a fourth. So this means we've multiplied the difficulty by a fourth in expectation. The trivial algorithm of sample a random code word and then test if its coordinates are valid, you'll have to repeat about 4 times before you get a valid solution. But we still have an easy problem. We've only multiplied the difficulty by 4. But this is why we chose a high dimensional code. So we just repeat this for all possible coordinates. For every single coordinate, we'll choose a random subset of the values for that coordinate that we'll say are valid. And a solution to our problem will be a code word whose each position is considered valid. And the hope is that the difficulty scales exponentially with the dimension. When we consider just x coordinates, we multiply by 2, y coordinates by 4. If we have 100 coordinates, the hope would be that we multiply the difficulty by 2 to the 100.
So Mark, the rate of the code is large enough that even after you place these constraints, there is a sort of a code word that satisfies.
Yes.
Okay.
Yeah. I won't really go into the exact parameters of the code in this talk, but you could think of the code as having rate somewhere around a half. There's a lot of flexibility actually in the rate of the code. But yes, it's a high rate code. So there will certainly be a lot of solutions, but hopefully this process has made it hard to find solutions, and certainly the trivial algorithm won't work.
Yeah.
Okay. So that's the problem we defined, and now the lingering questions are: why is it classically hard? We've explained why the trivial algorithm doesn't work, but maybe there's a more clever approach. The second question is, why on earth should this be quantumly easy? And then finally, both of these questions are potentially dependent on the choice of code. So we need to understand what code to use. All right, so let's start with classical hardness. We first note that our construction is a case of what I'll call a domain-constrained linear equation, where the goal is to find a solution to a linear system that also satisfies additional nonlinear constraints. These have some history in cryptography. For example, ITI considered random linear codes combined with a constraint on the L2 norm. The result is what's known as the short integer solution problem, one of the foundations of lattice cryptography. A more recent example considered in a few works is to take a random binary linear code and constrain to low Hamming weight. Both these sets of problems appear to be computationally intractable. And just in general, it seems that once you mix highly nonlinear constraints with linear equations, there's a chance to actually get some good hardness. Now, it turns out in our case, because we have this oracle around, we actually can prove unconditionally the classical hardness as long as we make an appropriate choice of code of our code. So first we have to give some notation and definitions. Given a word C and a product of sets S1 up to Sn, we can define the distance between C and the product as the fraction of symbols of C that are not in the corresponding set in the product. So some notion of distance between words and products of sets. And then we'll say that a code C is list recoverable. Here's a more precise thing, but I'll just say it in words. if for any product of small sets, S1 up to Sn, there are a relatively small number of code words with small distance from the product set. And note here that we don't care about, usually you would care about, in coding theory, usually care about the efficiency of doing your decoding. Here we actually don't care about the efficiency. We just really care about the fact that the set of code words of small distance is small. And note that list recoverability is a generalization of list decoding, where in list decoding, these SIs are just singletons. And list decoding, in turn, is a generalization of standard error correction, where the size of this set here is supposed to be 1. By generalizing to list decoding and then to list recoverability, we handle large sets, and we also allow for more flexibility in the parameters of our code by not insisting that the list size is 1. So error correction is of course very well studied. And list recoverability in particular has been studied in a few works. And there are a couple positive results here. The first example is by Guru Swami and Rudra, who showed that a code called the folded Reed-Solomon code is list recoverable. This is basically just Reed-Solomon, except where you take Reed-Solomon, you kind of package the symbols, the symbols of Reed-Solomon to groups, and then each group becomes a symbol of your new code. So it's basically just Reed-Solomon. And then more recently, Rudra and Wouters showed that a random linear code is also list recoverable. So what we show is that if C is list recoverable, then our problem is actually classically intractable. And we actually concretely give a success probability upper bound for any polynomial time adversary in terms of the parameters of the code. The intuition here is basically that list recoverability more or less corresponds to the trivial attack, or list recoverability more or less shows that the trivial attack is the only attack up to some sub-exponential loss to generate code words. It turns out you can do a bit better than just sampling random code words. You can choose your symbols carefully such that you can kind of test a sub-exponential number of code words all at once. But it's importantly sub-exponential, whereas the probability of any particular code word actually being valid is exponential in the dimension. And so we get that the overall probability of finding a valid code word is negligible.
So this is not under it's not under the assumption there's an oracle. This is just an absolute theorem.
No, it is relative to an oracle. Yes, so yeah, I guess my theorem here should have said classically intractable relative to a random.
So where does that come into your argument?
So basically the argument, so if you look at this expression here, it's a bit inaccurate, but so 2 to the n to the epsilon prime corresponds roughly to the number of code words that you can simultaneously test. And then there's a delta here, but let's ignore that. Sorry, 2 to the minus n is sort of the probability, and any particular code word is valid according to our notion of valid, which is defined relative to the random oracle.
So can I? So I want to ask a question a little similar to Shafi's, which is, okay. So first of all, just going back, your definition of list recoverable, I think I may have missed it. You're saying that there exists these parameters, delta, epsilon prime, whatever, such that for every set S1 up to Sn of a certain size, this holds. So
yes.
There's a quantity. Okay.
Yes.
And now, for your theorem, are you going to take these S's to be output of a random oracle, like? The S's are
the queries. The S's are the classical queries that the algorithm makes.
Yeah.
And then the list size roughly corresponds to the set of code words that are implicitly being tested by those queries. And then you basically just get a union bound. It's a little more complicated than that to handle adaptive queries, but more or less you get a union bound
So basically, you're saying that the definition of list recoverability is a definition with respect to an oracle.
The list recoverability is just a definition from coding theory.
But these sets are defined by an oracle, according to you. No?
No. The sets are the sets are domain elements
for
the random oracle.
Oh.
Right. So list recoverability is just a concept from error correction. There's no oracle or anything. It's just a property of the code. But we show that our problem defined relative to a random oracle is intractable classically if the code that we started from is list recoverable.
Okay.
Any other questions?
So just to make sure, you know, the proof for algorithms that make non-adaptive queries is just this, right? I mean, I look at all my queries to Oracle 1, 2, 3, they define the sets, and then you have to sort of figure out the probability that that these sets sort of hit code words, or they're close to code words somehow.
Close. Yeah, for non-adaptive queries, actually, all you care about is whether they hit code words.
Yeah, that's right.
You have to work a little harder for adaptive queries, and that's why you get this like delta n in the exponent. You know, you would sort of naively think it's only 2 to the minus n in the exponent. But when you move to adaptive queries, actually now you actually do start caring about the distance.
Right. Yeah, makes sense. Thanks.
Right. And I'll note that like this part of our construction actually parallels something that was already known. List recoverability was actually used before to construct classically hard hash functions. So Heitner et al. Used list recoverability to construct hash functions that were highly parallelizable. Our construction is different from theirs, but the sort of classical hardness proof follows similar ideas. The main novelty in our setting is really the next part, though, which is achieving quantum easiness. So let's jump into that. So our starting point is going to be a technique for what I'll call multiplying quantum states. And I don't know where the origins of this technique are, but it at least dates to Regev in 2005. So the setup is that we have 2 quantum states depicted here by plots where the horizontal axis I'm imagining is ranging over the possible outcomes of the quantum state, and the vertical axis are the amplitudes of those points. And the goal is to construct the product of the 2 states, where by product I mean that the resulting state, the amplitude on any point, is the product of the corresponding amplitudes of the 2 input states. Right here, so here's what this would look like in Ket notation. Now note that in Ket notation, I'm actually ignoring normalization here, and the normalization is in fact important. But for most of this talk, I'm going to kind of push that under the rug and ignore it, and generally be sloppy about my normalization. But just remember that it does come up when you dig into the details, and it is important. I'll say a tad more about this in a few slides. Okay, so this is the sort of high level goal, is to do this multiplication of quantum states. So the natural thing to do is to look in the Fourier domain using the quantum Fourier transform, which is one of the main tools in the algorithm toolbox. We might as well see what we can do with them. So if we were to apply, or if we were to look at the Fourier domain by applying the quantum Fourier transform, what happens? Well, if we treat the plots as a signal, what the QFT does is compute the state whose plot is the Fourier transform of the original signal. In our case, we had a Dirac comb and a Gaussian, and they map to a different Dirac comb and a different Gaussian with different parameters. Now, what happens to the product state? Well, this actually comes from the convolution theorem. So the convolution theorem says that the Fourier transform of the product is the Fourier transform of the product is the convolution of the Fourier transforms. So here in the Fourier domain, we get the convolution between our comb and our Gaussian. And in Ket notation, this actually has a nice representation where where basically we sum over all x, y pairs, where x came from the one signal, y came from the other. And every XY pair contributes a weight alpha hat X, beta hat X to the element X plus Y. So what this shows is that if we want to multiply quantum states, it suffices to convolve their Fourier transforms, where the convolution has this form. So this gives a blueprint for trying to multiply quantum states. So first step, you obtain your two states separately. And here we're just going to assume we're just going to work in the Fourier domain. So we're going to assume we have the two states in the Fourier domain. The second step is you do an addition and superposition because the convolution had this X plus Y term. So we take our states constructed separately, which have an X comma Y, and we just add in superposition to get X plus Y. Now we need this operation to be reversible for it to be a valid quantum operation. So really what we're doing is applying the map, which writes down X plus Y into some newly initialized registers and leaves the X comma Y behind. But now if we actually want the convolution, we need to somehow get rid of the X comma Y. You might be tempted to say, oh, you can just discard them, but that's not how it works. These X and Y and X plus Y are all entangled now. And if you try to discard X plus Y, you're gonna get junk. So we need to somehow eliminate them. And so what we're going to do is pretend, at least for the moment, that we actually can take X plus Y and could compute X comma Y from X plus Y. If we could do such a computation, then we do it, we basically apply it in reverse to uncompute the X comma Y values, and then we're left with the convolution.
So Mark, can I ask something? So yeah. You want the decoding to be efficient, right?
Yes, we'll want the decoding to be efficient. Yes.
Okay. All right.
All right. So in terms of these steps, first one is basically a given. We're just going to be given that we have these states. Usually, or either given or easy. In our examples, they'll be easy to construct. Adding and superposition is easy. The last one, though, not only might it be computationally intractable, but actually just might be impossible. It might be that there is not a unique X and Y for a given X plus Y, and it's not hard to come up with examples where that's the case. So this last step is kind of where all the difficulty comes in. Is this decoding of X plus Y into X and Y. All right, just to emphasize that decoding is not always possible. So we have our example from before. In this example, decoding actually is possible. If for any point on here, you actually, if you're in the spike here, if your X plus Y is in the spike here, you know that X actually came from the middle spike over here. And then just your distance from the center of this hump would tell you the Y value from the signal here. There's a slight tiny chance of error because of the tails of the Gaussian, they might overlap. But let's just pretend that's not a problem. And in fact, the error is so tiny that it effectively doesn't matter. But now suppose instead of these nice localized this nice localized comb on the left, I had something that looked more like this, and maybe my Gaussian's also a bit wider. Now my convolution is, it looks nice, but it's kind of a mess to try to do decoding. My humps now overlap significantly, and also my distance from the peak of a hump here might be due to my X being not at the peak over here, or might be due to my Y being not at the peak over here. And in general, for this example, you wouldn't be able to decode. So if these were your Fourier domain signals, you actually couldn't do the convolution. So with this in mind, I'll briefly explain Regev's application to this idea at a very high level. So what does he do? So in the primal domain, the first signal is going to just be the indicator for a linear code C. So it's just going to be the uniform superposition over code words. The second signal is just going to be some Gaussian weighted signal. Note here that it's a multidimensional Gaussian instead of one dimension. So this really is somewhat analogous to the example we just saw, except generalized to high dimensions. And what is the product? Well, the Gaussian forces us to have low norm. If we were to measure the state, it would basically, the Gaussian here only has significant weight on things with low norm, and the indicator for the linear code forces us to be in the code. So the product is actually a superposition of short vectors in the code, and if we measure that, we get a short vector in the code, which is solving cis. So what happens in the Fourier domain? Well, the Fourier transform of the indicator function for linear code is just the indicator for the dual code. Meanwhile, the Fourier transform of the Gaussian is a Gaussian. This is not quite accurate because it's really a discrete Gaussian and doesn't behave quite as nicely with Fourier transforms, but we can ignore that and just pretend that the Fourier transform is a Gaussian. And now, what is the decoding problem? It's you take a random code word in the dual, you add a Gaussian weighted noise to it, and you're asked to recover the original code word in the noise. And this is just this is basically just LWE, learning with errors. And so what Regev is able to conclude is that, well, if you could solve step 3, then you can actually solve cis. So under the assumed quantum hardness of cis, LWE must be hard. And this is the basis. This is the rough basis for Regev's reduction. Okay, so now that we've seen how to multiply quantum states, what we're going to attempt to do is the same thing, but for our problem, except here we actually do want to solve the decoding problem efficiently. So inspired by Regev's algorithm, what we're going to do, we're going to set our one state to be the superposition over code words. And we're going to set the other state to be the other constraint that we're imposing, which is the indicator for valid coordinates. So basically the superposition of valid vectors of coordinates, but over the the entire space as opposed to just code words. And the product of these will be exactly what we want. It'll be a superposition of solutions to our problem. So what's left to understand now is what is the decoding problem in the Fourier domain, and how can we solve this efficiently? So just for the linear part, just like Regev,
Mark, sorry.
Yeah.
Sorry, can you go back one slide?
Yes.
So the beta x are defined, these are going to be defined by a random oracle, is that right?
Yes, correct.
Okay.
Yes.
Thanks.
Okay,
sorry,
yes.
One more thing, Mark. So the beta x, the state can actually be computed efficiently, you're saying, because I do it for each coordinate separately and tensor.
Exactly. Right. Yeah, I didn't mention that, but yes. So the indicator, the superposition over code words, that's just linear algebra. That's easy. Yeah. And for the indicator for valid coordinates, we take advantage of the fact that basically it's a product state. So we can look at each coordinate separately, and all we have to do is generate the uniform superposition of all coordinates, test the oracle rejects, we throw it out and start again.
Yeah. Got it.
Okay. So for the linear part, just like in Regev, when you look at things in the Fourier domain, we just get the dual code. So that's easy. And for the valid coordinate part, things are different from Regev, and we hope they would be if we're going to solve this. So if we zoom in on just a single coordinate, the signal will look something like what I've depicted on the left here. It's just it's basically just a random. Every single horizontal position is just a random choice of 0 or 1 for the amplitude. Now, what's interesting is, so this is a mess here, but if you look at it in the Fourier domain, you get something really nice. The amplitudes actually converge to a very nice distribution that's highly concentrated around 0. About half of the overall weight will be at 0. So the 0 Fourier coefficient of a random function is about a half. And then all of the other values are just more or less uniformly distributed. Now, I will say there's a complex phase that occurs in all these other values. and you sort of need the complex phase in order to, like, because the Fourier transform can't lose information, and you need it to encode all the randomness in your primal domain, and that's where they show up, is in the phase, in the Fourier domain. But we won't care about the phase. All we actually care about is the amplitudes. So what does x plus y look like? Well, x is a dual code word, random dual code word, and y is just, for every coordinate, we have this error distribution where it's 0 with probability half and random with probability half. And so what we get is a dual code word plus random errors in about half the coordinates. And this is actually a very standard setting in error correction. Note that because the fraction of errors is could actually exceed a half, with reasonable probability, this is a setting where you can't do worst case decoding. There will be worst case errors that affect half the positions that actually result in the inability to uniquely decode. But what we can take advantage of is the fact that our errors are actually random. And so what we do is, we say if you can list decode for about let's say a half plus epsilon fraction of errors, if you can list decode, well, then actually with high probability your list will have size 1, and that's the answer for the decoding problem. So this is what we need in order to get our algorithm to work, is that you can efficiently list decode a half plus epsilon fraction of errors for the dual code. So now we have two constraints on our code. We need list recoverability in the primal domain, and a dual code needs to be efficiently list decodable. Now we talked about random linear codes before. Random linear codes won't work here. Essentially, the list decoding, it's information theoretically possible, but computationally intractable. This, roughly is analogous to the LPN problem. But the good news is that, yes.
Could we take a second just to pause and sort of talk about the analog to Regev, right?
Yes,
so,
sure.
What you're saying is that, like, morally, what the Regev step is letting you do is you get to take a superposition code words in the dual space, as well as like a superposition of like some error ball, and basically the ability to, in his setting, the CVP oracle lets you is the thing that lets you convolve these two, right? And you're setting
yes.
the unique decoding is the thing that lets you do the convolution.
Exactly. Yes. Good. So by a happy coincidence, random linear codes, the dual of a random linear code is another random linear code. So we would be happy sort of information theoretically, but we don't believe that you can efficiently do the decoding. But fortunately, the dual of a folded Reed-Solomon code, the other thing that we know is list recoverable, actually happens to be more or less another folded Reed-Solomon code, which has essentially optimal list decoding properties. And so that's going to be our code. There's going to be a folded Reed-Solomon code of an appropriate rate. In order, basically, we need the rate to be, a little less than a half in the rate of the dual code to be a little less than a half in order for us to be able to do the list decoding. And that's it. That's the specification of our problem.
So Mark, can you say what you need from the code again? I mean, do you need that if I pick a random code word in the dual and add half plus epsilon noise, I should be able to decode it to a unique
with high probability, yes. And that the fact that So list decoding is just potentially one way of doing the decoding. Really, what we need is exactly what you said, that taking a random code word and random errors, you can decode uniquely with high probability. There's actually some subtlety that I'll actually discuss on the next slide to that. And what we do is we show that it basically follows from list decoding, and and then sort of more generally, the rate of the code more or less implies that with random errors, the solution to list decoding will be a unique code word.
Do you really need it to be like really unique, or do you only need it to be like only one element in the list, which is like permitted by your rule?
No, because you actually need to do the uncomputation, right? So if we go back, if we go back here, we have X, Y.
Oh, because you're in the
X plus
dual.
Y, and
Because you're in the dual.
Yeah.
Okay, yeah.
Yeah, and we need to
Okay,
actually.
yeah. So you're actually like
X and
computing
Y.
phases. Yeah. Okay.
Okay, I do want to mention that there is a caveat to all of this, or things may seem easier than they actually are, and that's in general this with high probability bit is actually not necessarily good enough, and it has to do with this normalization that I've been sloppy about so far. So if you were to actually write down the convolution theorem, you do pick up a renormalization constant that's square root of n, where n is basically the size of the overall domain, which is huge. It's exponential. And what happens is when you try to actually analyze things, if you do it sort of the most natural way, your error terms, the probability that your decoding failed, ends up getting multiplied by the square root of n term, and suddenly non-negligible becomes noticeable, and potentially destroys the algorithm. And in Regev, this was actually also an issue, except that the Gaussians have such low weight in the tails that even after multiplying by the square root of n, you're actually still happy. In our case, our error probability is actually it's negligible, but it's still pretty high, and it's actually higher than 1 over n. And so if we were going to do things the naive way, we end up actually blowing things up and not getting not being able to justify the correctness of our algorithm. And so we needed to actually look a little more carefully at the exact error distribution you get, and sort of analyze things in a bit more delicate manner in order to justify that the errors actually do not blow up in our case.
So sort of, do you use the fact that sort of the errors cancel, you're using something about the decoding algorithm, the error distribution of the decoding algorithm, is that right? Or
yeah, it's I guess it's less about the I mean, our errors are, we can really think of our errors as uniform errors, but it's the particular structure of our problem that allows us to sort of show that even though the error rate is not too low, that the errors are sort of distributed in a way that makes things okay. And it's sort of a low level thing that I probably can't convey over the slides, but it's just I just want to point out that this state multiplying technique does potentially run into difficulties, and we ran into this difficulty in our work, but we were able to overcome it for our particular case. So I had prepared a number of slides kind of going into some more details on the applications. I don't know, now that we're somewhat over,
Yeah.
I don't know if we should just skip those. They're pretty high level. This what we saw so far was kind of the main idea of the paper.
So maybe I'm sure those would be relevant in once we get to either now or once we get to the panel. One way to do it is to go to the panel, and then you can talk about in the course of that, you can talk about the applications. How long would it take you to actually present those slides now?
It might 10 to 15 minutes, probably.
Maybe, we should have a bit of a discussion. So shall we start with the discussion and then jump back to those slides?
Sure, sounds good.
So do you have anything?
By the way, if you have to prioritize one, it seems like there is some confusion about how the results don't contradict AA. So maybe if you had slides prepared on the proof of randomness, that might be the most illuminating ones to highlight if you get to it.
Yeah, I mean, I could briefly talk about the proof of randomness. It's actually really, I mean, the proof of, yeah, the certifiable randomness is pretty easy, at least in the uniform setting. So literally what the proof of randomness is just Alice solves our problem. So here I wrote it in sort of like what the actual queries to the oracle would be. So she sends over a code word such that if the random oracle hashes of all the code words, all the symbols are 0. And here I'm prepending with the index, and this is to just ensure that all the different coordinates are independent. So she just solves an instance of our problem and sends it to the receiver. And all the receiver does to generate their random string is extract from the random string using a classical randomness extractor. Or not extract from the random string, extract from the solution to the problem to get a random string. And yeah, I didn't really go into explaining why in too much detail why the A conjecture implies this. But for intuition, suppose that our Alice was actually able to deterministically come up with a solution C. So what the A conjecture says is that if you look, so if Alice were able to deterministically come up with a code word satisfying our constraints, in particular, the first bit of that solution is also deterministic. And the A conjecture then says that, well, we had a quantum algorithm that deterministically produced some bit. Then there's a classical algorithm that's not too much slower that also produces approximately that bit. And you just repeat this for every single bit of the output, and you actually get a classical algorithm that will output the same answer as Alice. And so that's roughly the idea, is that, so for example, if the code word were actually computed deterministically, then it would be classically easy according to the AA conjecture. And we extend this idea to higher min entropy bounds to show that basically the solution C has to have significant min entropy. Otherwise, there's a classical algorithm. Otherwise, under the AA conjecture, there's a classical algorithm that violates our proof of hardness. And once you have C having min entropy, you're done. You just apply randomness extraction to get to a random string.
So sorry. So does this idea say something about the impossibility of sort of search to decision reductions? Is sort of what you seem to be saying, right? I
mean, it says if you have a search problem that's classically hard, if it's quantumly easy, the only way it can be quantumly easy is if the quantum algorithm is sort of sampling from a distribution with min entropy.
I see. Okay, thanks.
Great. Okay, wow. Thanks very much. That was really very lovely talk. Yeah, beautiful
Thank
ideas. At this point, maybe shall we move on to the panel?
Sure.
If you stop sharing your slides.